Hello everyone, welcome to Dr. A classes for BTech students. In this lesson, an introduction to hydrology, we will explore the fundamentals of hydrology. Understanding hydrology is crucial for civil engineering students as it plays a key role in water resource management, flood control, irrigation planning, and sustainable development. So, let us begin our journey into the science of water. Learning objectives of the course is understanding the scope, significance, and application of hydrology in water resource management, describing precipitation, runoff, infiltration, evaporation, and groundwater flow, understanding methods for estimating water yield, distribution, and occurrence in a basin, using hydrological principles for designing dams, drainage systems, and flood control structures, understanding how climate, land use, and soil characteristics affects the hydrological cycle. These objectives will provide a foundation for applying hydrological knowledge in civil and environmental engineering projects. What is hydrology? Water exists on Earth in solid, liquid, and gaseous state, and hydrology is the study of water in all these phases. Water is one of the most essential components of Earth's system, existing in three primary states: ice, water, and water vapor. The movement, distribution, and properties of water in these different states play a crucial role in shaping our environment. This field examines how water circulates through the atmosphere, surface, and subsurface, influencing weather pattern, ecosystem, and human activities. The term hydrology is derived from the Greek word hydro, meaning water, and logos, meaning study or discourse. Thus, hydrology is fundamentally the study of water, its behavior, and its interactions with the Earth's system. Hydrology examines the occurrence, circulation, and distribution of water on Earth and in the atmosphere. What is engineering hydrology? Engineering hydrology, also known as applied hydrology, is the branch of hydrology that focuses on the practical application of water science in engineering. It involves the study and management of water resources to support infrastructure development, environmental sustainability, and disaster mitigation. It includes estimation of water resources, assessing the availability and distribution of water, analysis of hydrological processes, studying precipitation, runoff, infiltration, evaporation, and their interactions, management of flood and drought, analyzing extreme hydrological events, and developing mitigation strategies, water resource planning, designing dams, reservoirs, drainage system, and irrigation networks. It is essential for managing water sustainability, preventing water-related hazards, and supporting various civil engineering projects. This field plays a vital role in water resource management, infrastructure design, and disaster mitigation. Scope of engineering hydrology. The study of engineering hydrology provides essential knowledge for designing water-related infrastructure and managing resources effectively. It helps in flood prediction and control, determining the maximum probable flood and its frequency for designing safe drains, culverts, dams, reservoirs, and flood control structures. Water resource estimation, assessing the yield from a basin including occurrence, quantity, and frequency for designing dams, municipal water supply systems, hydropower projects, and river navigation. Groundwater development, understanding hydrogeology including soil formation, recharge surfaces, rainfall patterns, and land use for efficient groundwater extraction and management. stormwater management, identifying maximum storm intensity and frequency for designing effective drain systems. Engineering hydrology is therefore crucial for water resource planning, infrastructure, safety, and sustainable development. Hydrological cycle. The hydrological cycle or water cycle is the continuous movement of water on, above, and below Earth's surface. Driven by the sun, water evaporates from oceans, lakes, and rivers, rising as vapor. It condenses into clouds and falls back as precipitation, such as rain, snow, sleet, or hail. This water either evaporates again or infiltrates the ground or flows into rivers and oceans, completing the cycle. The hydrological cycle is an unending process because it is a continuous movement of water within the Earth's atmosphere, surface, and underground. Since water is neither created nor destroyed in this cycle, it keeps circulating through different states, liquid, solid, and gas, maintaining Earth's water balance. Components of hydrological cycle. The components of hydrological cycle are evaporation. The sun's heat causes water from oceans, lakes, rivers, and soils to turn into water vapor and rise into the atmosphere. Condensation. Water vapor cools and changes into tiny liquid droplets, forming clouds in the atmosphere. Precipitation. When water droplets in clouds grow too heavy, they fall to earth as rain, snow, sleet, or hail. Infiltration and percolation. Water seeps into the soil and moves deeper through porous rock layers to replenish groundwater. Runoff. Excess water flows over the land into streams, rivers, and lakes, eventually reaching the ocean. Transpiration. Plant absorbs water through their roots and release it as vapor into the atmosphere through their leaves. Human impact on hydrological cycle. Deforestation. The removal of trees reduces transpiration, leading to lower humidity, altered precipitation pattern, and disrupted local water cycles. Urbanization. The replacement of natural land with concrete and asphalt increases surface runoff, reduces infiltration, and raises the risk of flooding and water pollution. Climate change. Rising global temperatures alter evaporation rates, shifts precipitation patterns, intensify extreme weather events, and impact water availability. Water extractions, excessive withdrawal of groundwater for agriculture, industry, and human consumptions lower water tables, depletes aquifer, and can cause land subsidence. Natural disaster and water cycle. Disruptions in the water cycle and their consequences. Floods, increased evaporation and extreme precipitation cause intense rainfall, while deforestation and urbanization reduces infiltration, leading to flash floods. Drought, altered evaporation and precipitation patterns, groundwater depletion and deforestation reduce water availability, intensifying dry conditions. Extreme weather, warm oceans, fuel strong storm, shifting atmospheric pattern cause prolonged heat waves and rising sea levels, increase coastal flooding. Climate change intensifies these effects. Rising global temperature accelerate evaporation, altering precipitation and increasing drought and flood risk. Warmer oceans and changing atmospheric currents intensify hurricane, storm, and extreme weather events worldwide. Global water distribution and hydrological cycle. The exact amounts of water in different components of the hydrological cycle are still not precisely known. Most of the Earth's water is stored in oceans, glaciers, and groundwater, with only a small fraction in surface and atmospheric water systems. Global water distribution. 97.5% of Earth's total water is in the oceans. This water is saline and unsuitable for direct human consumption, agriculture, or most industrial uses without desalination. Theoretical coverage. If the Earth's surface were perfectly smooth, the existing ocean water would create a global ocean approximately 2.6 km deep, covering the entire planet. The remaining 2.5% is freshwater, but most of it is not easily accessible because most of it is stored in polar ice, glaciers, and deep underground aquifers, making it difficult to access for direct use. The readily available freshwater for human use accounts for less than 1% of the total freshwater, emphasizing the need for sustainable water management and conservation. Freshwater distribution. Although 71% of Earth's surface is covered by water, only 2.5% of it is freshwater, and most of it is not easily accessible for human use. 68.7% of the total freshwater is in polar ice caps and glaciers, mainly in Antarctica and Greenland. 30.1% of freshwater is groundwater, extending 200 to 600 meters below the surface and serving as a key source for drinking water and irrigation. Only 1.2% of the freshwater is found in surface water and other sources, including lakes, rivers, soil moisture, and atmospheric water. Surface freshwater breakdown. Freshwater is a vital source, but its availability is unevenly distributed across different reservoirs. The majority of surface freshwater is locked in ice, while only a small fraction is easily accessible for human use. 69% of surface freshwater is stored in ice and snow, primarily in glaciers and polar ice caps. 21% of surface freshwater is found in lakes, which are essential for drinking water and ecosystem. 4% of surface freshwater exists in rivers, playing a crucial role in hydrological cycle and human activities. 6% of surface freshwater is present in soil moisture, the atmosphere, and living organisms influencing plant growth and weather pattern. Surface water distribution. Surface water plays a crucial role in hydrological cycle. However, its distribution is highly uneven across different reservoirs. Lakes hold 87%, the largest share of surface water of serving as primary source of drinking, irrigation and ecosystem. Swamps and marshes hold 11% of the surface water. Wetlands store a significant amount of surface water acting as natural filters and flood control systems. Rivers, though holding just 2% of surface water, are lifeline for water supply, transportation and biodiversity. So, the proper management of surface water resources is essential to ensure sustainable water availability for future generations. Self-assessment questions. At the end of the presentation, these are self-assessment questions. Go through each question carefully. Answer these questions based on understanding of the topic. Review any concept you are unsure about. The questions are: what is hydrology and why is it important in engineering? Define the hydrological cycle and its main components. Why is the hydrological cycle considered a closed system at a global scale? How does human activity impact the hydrological cycle? How does climate change affect the hydrological cycle? What is the role of engineering hydrology in flood control and water conservation? Thank you for joining this lesson on engineering hydrology today. Hope you found this presentation informative. Don't forget to like and subscribe the channel Dr. A Classes for more engaging lessons on core subjects of civil engineering. Thank you.